Alrighty, hello my people, I hope we're doing well. I'm going to go ahead and continue on with these examples of integration by parts. This one right here is a little bit trickier than the past because instead of x, we have x squared. Now, the thing is that when you assign u to be sine, or even dv to be sine, you know that as you take the derivative or antiderivative, it's just going to flip-flop back and forth between sine and cosine, negatives and positives, right? The only hope you have of getting to an integral that is integrable is to get rid of x squared. And the only real way to get rid of x squared is to basically constantly take its derivative, right? So let's let our u be x squared and our dv be sine x dx. Okay, so let's go ahead and take the derivative of x squared, becomes 2x dx, and when I take the antiderivative of sine, I recognize the fact that it's going to be negative cosine. Okay, so that winds up being negative x squared cosine x, and usually it's subtracting the integral, but the integral itself is going to have a negative in it as well, so it's going to be minus a negative, so let's just go ahead and add. We'll pull the 2 out in front, and that becomes x cosine x dx. Now, that is not integrable, right? In fact, we actually did this one earlier. It was the second one that we did. But in the process of using integration by parts, I have actually gotten closer, right? I've actually gotten closer to something that's integrable because I've taken x squared and I've gotten it reduced to just x. So what we need to do is we just need to do it again. Okay, and we know how to do this because we've done it earlier. So u is equal to x and dv is equal to cosine x dx. When I differentiate cosine, it just becomes sine, and when I differentiate x, it becomes dx, right? This integral is that basically designation of u and dv in parts. Now you can use separate variables if you want, but basically it just, I just group them and point them to what exactly they are associated with, and I think the confusion is minimal when you do it that way. But remember this 2 that's sitting out right here, remember that that's going to have to be multiplied by both terms. So my uv is x sine x, and then of course my v du is sine x dx. I'm going to have negative x squared cosine x plus 2x sine x. And basically sine, when you anti-differentiate it, remember, becomes negative cosine. Well, that negative is going to cancel with the negative out in front there, so it's going to be plus 2 cosine x plus c. And that right there is messy, but correct, okay? And basically all you had to do was you had to do parts twice. And that's, it's, not fun. In a later lecture, we're going to talk about the tabular method, which basically, and this should come as no surprise, when you do the same thing over and over and over again, sometimes there's a formula or a method that you can use to sort of do things iteratively, and you can actually wind up doing integration by parts in a tabular format. So basically you just dump it into a table, and as long as you set the table up correctly, you get the right answer. Now this one, instead of x squared times sine x, it's x sine squared x dx. Okay, this one actually is really, really difficult because you want to split it up into pieces, right? You're like, well, I have 2 different factors. One is an x and one is a sine squared. But let's go ahead and see what happens if we designate u is equal to x, and therefore we have to designate dv as sine squared x dx. I don't know how to do that. Okay, and in fact, when we get to the next section, that basically on trig integrals, we'll deal with stuff like this. But at present, I mean, you can get your du, and that gives you the dx, but v, you're kind of like, huh? Okay? So you go, okay, well, maybe I can go the other way, right? Maybe I can go the other way and designate u as sine squared, and dv becomes x dx, right? That's how I did it with the natural log. Well, the great thing about the natural log is that when it's differentiated, it becomes 1 over x, and it cancels out with the increasing degree when you start putting the x over here. Unfortunately, that isn't the case here, and this becomes 2 sine x cosine x dx, okay? Which, of course, is sine 2x dx. Now, you could kind of go forward in this way, because that can become, 1/2 x squared sine squared x, and when you multiply these two together, you're going to get 1/2 x squared sine 2x dx. And the only thing which makes this different from the previous problem is you just have an angle measurement expression that's different. It's 2x instead of x. So as you go ahead and designate again over here, u becomes, x squared, and du becomes sine 2x dx. And when you anti-differentiate from here, or sorry, this is dv, v becomes, negative 1/2 cosine of 2x, and du becomes 2x dx. You could even alternatively designate u as x sine squared x, and then dv just as dx. But all of these wind up being really, really not fun options. And problems like this we'll see, and we'll revisit this one when we get to the next section. Problems like this are better resolved by using trig IDs up front to simplify the integrand, rather than trying to muscle it with parts. I mean, I've given you two different strategies of how to do it by parts, and it works. By the way, this derivative right here is just nasty. I mean, it's sine squared x plus 2x sine x cosine x dx. I mean, it's nasty. But I just wanted to show you something like this, that when you wind up with something that messy or involves that many tweaks and turns, the odds are that one of the other methods that we'll be learning in this chapter winds up serving you a little bit better. Okay? Now, let's look at this one. If I'm trying to determine what my u is and what my v is, now I'm looking at x squared, and I'm like, gosh, I'd really like that to go away. I'd really like that to be my u and become 2x down here when I find du. But if I put x squared here, I have to put arctan over here. And we don't know how to integrate arctan yet, okay? And so basically what you're going to have to do is you're at least going to have to entertain the possibility that arctan goes over here and x squared dx goes over here. And I don't like doing that because I don't like the degree increasing, right? The degree increasing seems like a step backward, but it's the degree increasing, but I have now changed an inverse trig expression into something that is rational, and that is a huge step forward, right? And so it may kind of bug some people, some students, to actually do that, but it winds up being the actual way that it needs to happen, and you end up getting x cubed over 1 plus x squared dx. Now that's nasty and it's not fun, but it's certainly better than that. Okay. What we need to do now is a strategy that we employed on a previous one, and that is this becomes integration by substitution. And we'll use t again, and I'll put this in block letters so it's a little bit easier to see that I'm actually writing let. So let t equal to 1 plus x squared. Now, if that's the case, then x squared is equal to t minus 1. Remember when we did integration by substitution, you had those problems where sometimes you had to back substitute? Because if you have 1 plus x squared down here, there's only a handful of options, right? It's either inverse trig, which it's not because that numerator is of too large a degree, or it's natural log. But again, the numerator is of too large a degree. But if I can split this apart and instead of x cubed over 1 plus x squared, I can think of it as x squared times x over 1 plus x squared, then I can actually transform it into a rational expression that is integrable. And if I do that, I can split up the x squared and the x. So let's think about it this way. If I have the integral of x cubed over 1 plus x squared, let's think about this as, well, if I need an x. I can take one of those x's from that x cubed and couple it with a 2, right? And if I couple it with a 2, then I'm going to need to go ahead and multiply by 1/2 as well to compensate, so I don't change the value. But what's left over after I use one of the x's from the x cubed is that x squared. And therefore, I have that integral, and when I transform it into my t values right here, I have 1/2. This is my dt, so it can sort of move out over here. I'm going to get t minus 1 over t dt, or 1/2 the integral of 1 minus 1 over t dt. I can go ahead and do that term by term. And that winds up being t minus the natural log of the absolute value of t plus c. Well, you're not going to need the absolute value because t is x squared plus 1, and that's never negative, right? And so what I have here is I have 1/2 x squared plus 1, or 1 plus x squared, whichever you want, minus 1/2 natural log of x squared plus 1 plus c. Now this right here is this integral. So we just get 1/3 x cubed arctan x minus, and of course the 1/3 needs to be distributed over both of these terms, and it's a negative 1/3, so I get 1/6 x squared plus 1 plus 1/6 natural log of x squared plus 1 plus c. And basically what happened is you used parts to get an integral that actually was u sub, but it was one of those unique u subs where you actually have to do this right here so that you can back substitute in for sort of factors that are not just satisfied regularly. Now, here's the thing. If you saw this in the back of the book, it might not have this plus 1 right here. Because if you distribute this negative 1/6 across x squared plus 1, you're going to get a negative 1/6, and then that can just be absorbed into c. But I've left it here simply because there's that certain symmetry between those terms right there, because that's where you plugged in for t both times. I'm hoping that there's just lots and lots and lots of ways for this strategy not only to be employed, but also to be blended in with other strategies. So integration by parts isn't necessarily just integration by parts. Sometimes it's integration by parts which lead to substitution. Sometimes it's substitution which leads to integration by parts. Sometimes it's integration by parts involved with trig identities. So it'll involve the strategies we're learning in this section along with the strategies we're learning in the next section. All right, this one. This is going to appear to go nowhere. Because if you think about it, if you designate u as e to the x, then every single derivative is going to be e to the x, e to the x, e to the x, e to the x. If you designate u as sine x, then it's going to be, its derivative is going to be cosine x, and then its derivative is going to be negative sine x, and then its derivative is going to be negative cosine x. So both of them, neither of them seem to disappear in the way that, x squared would. Like x squared, you just do 2 iterations and it dissolves, and now you have an integral that is integrable. Well, let's go ahead and see how things shake out, okay? Let's, since we tend to be better with differentiation, and the trig function not only goes back and forth between sine and cosine, it flip-flops between positive and negative. Let's actually deal with the positive and negative flip-flop in differentiation rather than in anti-differentiation. And we'll designate e to the x dx over here as dv. That makes the anti-differentiation very easy each time, and it just becomes e to the x. And this becomes cosine x dx. And some of you are thinking, he said each time, so I guess we're going to be doing this more than once. Yes, we are. And this becomes e to the x cosine x dx, right? Because this is my uv minus the integral of v, which is e to the x, and then du. Well, this right here, I used those designations. Let's do it again. Now, don't flip back to using e to the x. Basically, you want to be consistent. If you designated the trig function as u last time, you need to do it again this time. Now, this integral right here is going to be this part's designation. Now, the derivative of cosine is negative sine. But, the antiderivative of e to the x is still e to the x, okay? So we have e to the x sine x minus. Now remember, this negative is going to need to be distributed because when you do parts, you have a difference here, right? So it's going to be uv, so e to the x cosine x minus the integral of e to the x times negative sine x dx. Well, the minus out in front and the negative in the integrand can cancel out and become e to the x sine x dx. Okay, well, let's go ahead and distribute that negative. And you're like, well, that's no good. I'm right back where I started. But this whole thing is equal to that. So can I add this integral to both sides and wind up with 2 times the integral of e to the x sine x dx is equal to e to the x sine x minus cosine x plus c? And the answer is yes, okay? Because remember, understood to be over here is this integral. If those are exactly the same, I can just add it to both sides. In adding it to both sides, it gets rid of this one on the right-hand side, and it doubles the one on the left-hand side. And then the only thing that's left to do is just divide by 2. And so the integral that seemed to be going nowhere, you actually never wound up integrating in the sense of you never wound up finding an integral that was integrable. Basically, you wound up doing parts until you ran into one that duplicated the one on the left-hand side of the equation, and then you simply combined them and divided by the coefficient. And you got to admit, that's pretty cool. All right, let me see what we have left to do. Let's do one more, and then we'll pause and we'll call this video to a halt, and we'll do some definite integrals in the next one. Okay. Now this one right here, we've seen one where we did parts, and the parts led us to an integral that was doable, but had to be done by substitution. This one is one that actually requires substitution before we start doing the parts. So I see the fact that I have e to the negative t squared, and when you're doing u substitution, it's always easiest just to assume that it's the inside of the visible composite function that's going to be your u. So we get, negative t squared. And if that's the case, then du is equal to negative 2t dt. Okay, well, if negative t squared is u, then obviously t squared is equal to negative u. Okay. Well, if that's the case, then I can change this whole thing up because I can actually pull t cubed apart, and t cubed can become t squared and t, and e to the negative t squared dt. Now that's a good thing because remember that negative t squared is u. So if I do a negative right here and a negative 2 right here, the negatives will cancel each other out, and the only thing that's left to do in order to compensate for the fact that I've included a 2 is to put a 1/2 out in front. Now, let's go ahead and reorder that a little bit, and I get e to the negative t squared, negative t squared, and negative 2t dt. That becomes e to the u times u times du. And that can be done by parts. Let's call it, instead of u and v, let's call it a and b, since we're already using u right here. So my a can be my u, my db can be my e to the u du. Anti-differentiate, that becomes e to the u. Differentiate this, that becomes du, right? And so what I have here is I have 1/2 u e to the u minus e to the u du. And we've done this before. I mean, this was the first one that we did. U e to the u. And then, of course, this is going to be minus 1/2 e to the u e to the u plus c. Well, that u, okay, that u winds up being negative t squared, and so I'm going to get negative 1/2 t squared e to the negative t squared minus 1/2 e to the negative t squared plus c. And all that was instead of doing parts and winding up with that residual integral that was substitution, we actually needed the substitution to get us to here so we could recognize the fact that what we needed to do was use parts. Okay, we're going to call this video to a close, and I'll do some definite integrals and introduce you to the tabular method in the next video or two. I haven't decided. Depends on how long the problems take. But 1 or 2 more videos, and those are the 2 topics that are left. If you have any questions, please do shoot me an email. Bye.